volevamo avvisarvi di questo possibile inconveniente. Non dovrebbe essere una cosa major, dovrebbe consentire comunque a tutti di continuare a seguire l'evento. E se ci siamo tutti più o meno, io comincerei. È un piacere di avere qui Francesca Toni oggi pomeriggio. Francesca è professore in Computational Logic, è Royal Academy of Engineering and JP Morgan Chair in Argumentation-Based Interactive Explainable AI nel Dipartimento di Computing dell'Imperial College di Londra. Francesca si è laureata a Pisa, poi ha ottenuto un PhD a Imperial College, è la coordinatrice, la leader di un research group che si chiama CLARG, che vuol dire Computational Logic and Argumentation. Ha coordinato un grande numero di progetti europei, è stata anche nominata Fellow della EUR-AI nel 2019 e recentemente ha ricevuto un ERC Advanced Grant. Ha pubblicato tantissimi articoli, credo 200, scritto sulla short bio, e ha anche fatto ottimo servizio alla comunità scientifica sia come organizzatrice e chair in importanti conferenze che come editor di importanti journals scientifici. E il talk today, scusate, io mi sto italiano in inglese. Il talk oggi riguarderà Explainable AI via Computational Argumentation, vedete il titolo sulla prima slide. Sono veramente contenta di darti il benvenuto e the floor is yours.
Io ringrazio te e ringrazio Sabina per l'invito, è un vero piacere e anche un onore essere qua. Mi cimento con l'italiano, c'è qualcuno che preferisce l'inglese? Inglese. That's great. Great to hear. I have an excuse. My Italian is still pretty much, my English is still pretty much Italian, but I'm not that used to speaking about work in Italian, so I'm great. Right, I'm going to speak about explainable AI by means of computational argumentation, and I'm going to first tell you a little bit, first hiccup, su. Sì, sto pigiando il tasto giù, però non va.
Guardare il suo e spingere.
Questo, sì, ma non va. Sì. Ah, ok.
Francesca,
No problem.
Di parlare relativamente vicino.
Ok.
Perché...
Benissimo. Okay, I'm going to tell you a little bit first about the methodology I'm deploying in a lot of the research I'm doing, and that is computational argumentation. This is something within the field of AI in general, at the intersection of a number of areas, in particular, knowledge representation and reasoning, multi-agent systems, and natural language processing. So these three areas all contribute to the field of computational argumentation. I'm going to tell you how to go about using computational argumentation for supporting the vision of explainable AI. But first, I'm going to tell you a little bit about explainable AI, what is out there, and what we are trying to contribute within this field itself. So the two things put together, computational argumentation and explainable AI, allow to support a number of applications. And I'm going to focus here on a number of examples of the kind of things we can do using computational argumentation for explainable AI. Can you hear clearly? Am I? Okay. Great. So let us start with computational argumentation. In a nutshell, this is about identifying argumentation frameworks, their semantics, and studying properties of this combination of the frameworks with the semantics. In a nutshell, the frameworks are basically abstractions of debates. At the heart of debates, there is conflict, and conflict is crucial and core within computational argumentation. Semantics are just ways to evaluate these debates. And properties are ways to sanction goodness of semantics in general and in particular for certain applications. So I'm going to give you some examples of what this general vision is. I'm going to start with potentially the most well-known and one of the most influential approaches within computational argumentation, and this is Dung's abstract argumentation. It's an approach that dates back to 1995, but was recently awarded the AI Journal Classic Paper Award. So it's still very much going strong. So within abstract argumentation, frameworks can be just seen as a graph. The nodes of the graph are arguments. We don't care what they are. We don't care what they look like. They're just arguments. The focus of the framework is on the conflict, the relationships between these arguments, which are just the edges of these graphs, that represent disagreement, or as we call it in jargon, attack. So these graphs are just basically abstractions of debates, focusing on disagreement points in these debates. An example of use of this kind of framework is, for example, in modeling reasoning with policies. This is the policy that my bank has, or had before Brexit, for breakdown cover. You can see I have underlined some bits of it, sanctioning when an account holder is covered by the policy and when the account holder is not covered by the policy. So in particular, I'm covered if I'm traveling in a private car when it breaks down, but I'm not covered if the car is not registered to an account holder, unless the account holder is in the car, so me in this case, is in the car when the car breaks down. So you can see that there are different rules that are underpinning this policy, and these different rules may give rise to debates, if you like, concerning as to whether I'm covered or somebody who is an account holder is covered or not. So in particular, if there is some account holder, Mary, who is traveling in a friend's car when the car breaks down, and we need to decide whether she's covered by this policy or not, you can create a debate whereby there is an argument for Mary to be covered, which is given by what's on the left-hand side there, and that's supported by the fact that she's traveling in a private car. There is an argument against this argument, saying that actually she's not covered because the car is not registered to her, and that's the first bit on the right. But there is an argument against this argument that says she was actually in the car at the time of the breakdown, and therefore she should be covered. So this is a way to use an argumentation framework, an abstract one in this case, as an abstraction of reasoning with a policy. It's just an example and an application. So once one has obtained these frameworks, then of course one needs to decide what to do with them. They're not just ways to represent information, you want to use them somehow. And the semantics is what allows you to draw conclusions. So semantics, in the simplest case, can be seen as recipes for determining sets of winning arguments. So in particular, with this very simple graph, you could determine that the black argument on the left is a winning argument because nobody objects against the argument. The purple one in the middle is losing, is a bad argument because it's attacked by a winning argument. And the blue one, the grayish one on the right, is a winning argument again because it's defended against the attacker by a winning argument, or it's attacked by a losing argument. So these semantics can then be used to basically support decisions in the case of reasoning with policies. For example, in our simple kind of instantiation we've seen before, we can use the winning arguments to determine whether the particular customer is covered or not. And in this particular case, because the argument sanctioning that she's covered is winning, you can draw the conclusion that she is indeed covered. So this is a very simple example of what these frameworks are about. The properties are just ways to say, the semantics is a good thing. In this particular case, you may be interested in existence. You always want to be able to decide for a customer whether they're covered or not, and therefore it's important that the semantics is, exists. You can decide what is winning or not. But there may be other properties as well. This is just an example. There are others, and I have this slide here going back to the good old days of logic programming. I've got this slide for Franco, so Franco, please pay attention here. You can actually instantiate these frameworks with logical rules and obtain arguments that are built from logic programs. I'm not going to give you the details, but it's another kind of framework. And then you can actually also instantiate these frameworks in all sorts of ways that got nothing to do with policies of logical rules. For example, we use them to explain why schedules computed by standard optimization techniques are not optimal or semi-optimal. And we map schedules into argumentation frameworks, and then the semantics tells us what is non-optimal or optimal. And then we use these frameworks for explanation. I won't give the details, but I'm going to move on to the kind of framework we use extensively for explainable AI, and that's bipolar kind of argumentation, where in addition to disagreement, you can also have agreement or support between arguments. So here, the double line, the double arrow indicates support. So the green argument is supporting the blue argument. In debates, you don't just have disagreement. In debates, you also have agreement. I say something, some of you may disagree with me, and some of you may agree with me. So you need to also allow to accommodate this kind of, relation as well. And in the case of these kind of frameworks, for example, are very useful for resolving conflicts that may arise in textual reviews. This is an example of a bipolar argumentation framework that I have drawn by hand from a bunch of reviews for this book. I have drawn this by hand in this particular case, identifying the kind of relations, bits that are in support of reading the book, bits that are against reading the books, and also relationship potentially between different statements within the reviews. I've done it by hand, but there is a whole area within computational linguistics, within natural language processing, called argument mining, that is actually looking at automatically extracting this kind of bipolar argumentation frameworks from text using standard machine learning techniques. And my group has produced a bunch of techniques for doing this. What's important here, my focus is on showing you how this kind of framework can provide a way to abstract away from information and the semantics, and in particular, gradual semantics, another form of semantics for bipolar argumentation framework, can kind of help us doing this. Here, in this particular setting, I'm adding to the bipolar argumentation framework some quantities, so we call them quantified frameworks, which in the case of the reviews may correspond to votes that people may provide for different reviews. In this particular case, 3 people liked it and 3 people disliked this. So you can extract some kind of numerical assessment of the goodness of the arguments prior to debate. This is something we call intrinsic strength or base score. In this particular illustration, I'm using numbers between 0 and 1. And I have decided they were all 0.5 here, but in general, you may want to have different numbers depending on the aggregation of the votes. So, as I said, once you have extracted these frameworks, that's not the end of the story. You want to do stuff with these frameworks. So the kind of stuff you may want to do is, again, empowered by semantics, which are ways to evaluate the debates. In the particular case of quantitative bipolar argumentation framework, we define what we call gradual semantics that ascribe a dialectical strength to the argument. This dialectical strength, and I'm not giving you the algorithms and the formulas, I'm just giving you the intuition here. These numbers are somewhat reflecting how strong these opinions are in the context of the debates, taking into account how strong they were when they started. And an important aspect of this kind of semantics, gradual semantics, that instead of just saying these arguments win, these arguments lose, tell you how strong they are, giving them a number, one of the important things is that these ways to calculate the number reflect dialectically meaningful properties. This is just an example of what we can do with this semantics. We can basically take the debates, extract the framework, and then apply the semantics. Here I'm using a system that we have defined ourselves for evaluating the dialectical strength. And you can see that given this debate, the dialectical strength is quite high for this book, despite the disagreement, because there is a lot of support and there is a lot of support for support. So this is a way basically to say, given all this information, which is not a lot, but still it takes some time to parse, you can extract an abstraction that then paves the way towards a decision, helping you deciding what to do. And something very important of the semantics, again, are the properties. In the particular case of gradual semantics, the properties need somewhat to reflect the kind of behavior you would expect from human debates. And in human debates, for example, you would say that if somebody disagrees with you publicly, it weakens your position. And if somebody agrees with you publicly, then they strengthen your position. So it's important that this semantics, this way to compute the numbers that correspond to the dialectical strength, these numbers reflect these properties to make dialectical sense. You wouldn't want to trust a system that claims to be arguing if the argumentation was not one that you would buy. And these properties are what makes this argumentation viable in a sense. Okay, so this is, we have lots of applications. This is an example of the application of this quantified bipolar argumentation in engineering, design, in particular to decide what type of foundations a certain building should have. I'm not going to give you details, but just to tell you that there are a bunch of possible applications. This concludes the introduction to the computational argumentation. There is a lot more I could tell you, but I just wanted to give you a general idea. Are there any questions now before I move on? Or shall I take questions at the end? What do you prefer? Okay, I'm happy to take questions anytime, so don't be shy. Okay, so now computational argumentation is a generic methodology with lots and lots of things. Dino, you have a question? You were waving. Oh, okay, great. Okay, right. So what I'm going to talk to you about from now on is how to use this computational argumentation to support explainable AI. Explainable AI, very hot topic. There is a lot going on at the moment in this space. It's actually something that has been around in AI for a long time. As soon as you want to deploy AI to support applications, you need to be able to produce solutions that are explainable, that humans can understand. The economists put it very nicely last year. That AI, yes, it can do a lot, but it can work best when when humans can hold its hand and can understand, therefore, what it is doing. So explainable AI, as I said, has been around for a long time. At the time of expert systems, there was a lot of work on explainability, so it's nothing new. But nowadays, the use of techniques in AI that are data-driven and they are very opaque have made the necessity of explainable AI even more important. There is legislation that pushes towards explainable AI. GDPR, for example, has been interpreted as pushing towards explainability. There are guidelines that push towards explainable AI to guarantee trustworthiness of AI systems. And there are countries and governments, for example, in the UK, there are, there is a general tendency towards pushing in this direction. So you want AI that you can understand and that can explain what it does. And because of this obvious need for explainable AI, there are lots of solutions. So there is, I'm focusing here on illustrating solutions that provide local explanations for outputs computed by machines for inputs. For example, you could have a machine learning method that processes credit card applications, and in this particular case, denies a particular application. So the idea is that you want to understand why this application for a credit card was denied, and you want to tailor the explanation to the specific audience, beneficiaries of your system. And there are very many types of explanations that have been defined in the literature, for example, attribution-based, counterfactual, rule-based, to name a few. Just to give you an example, we, as an attribution-based explanation, a kind of factual explanation, you could obtain that the card application was denied because the client is credit unworthy. So this is the main reason for the decision, despite good salary. So this kind of explanations that include line and sharp amongst the several popular ones are basically telling you the reasons for and the reasons against. And this is very important what I'm telling you, because you can already see that I'm giving this an argumentative reading. These are reasons for and reasons against that output. You also have counterfactual explanations that, instead of pointing to the reasons for and against, tell you what could be changed to guarantee a different output. So in this particular case, you could say that had the client had a good credit score, then the application would have been granted. So here, the counterfactual explanation is about, what could change so that you would change the output as well. And then there are, other types, including there are a bunch of people that work on this. These are just the first, then there are lots more people. And then there are, of course, rule-based explanations, which package somewhat this information into rules and then potentially try to generalize these rules, and anchors and also the work that is happening here with Fosca and Dina's group are following this line, and these rules can have both a factual or attribution-based flavor as well as a counterfactual flavor. So these are a bunch of existing approaches. So is there need for more? Are we all happy? Are we all satisfied with this? Well, there is a bit of a problem, I would say, that identified by several, including myself, which is that these explanations really cannot just focus on the machine side of things. They cannot just focus on what experts, developers of machine learning techniques would buy. They also need to focus on the users. And in particular, you need to have a kind of an understanding of what humans like, appreciate, buy as explanations before you can design explanations for machines themselves. So Tim Miller, for example, has written an interesting survey not long ago, looking at literature in the social sciences for explanations to humans. So the view here is that you can't just have machine learning. You need to put together also the social sciences and have a holistic, if you like, combined approach. And in the context of the social sciences, there is also a kind of a good understanding that in order to build explanations, you need to understand how people communicate these explanations themselves, and argumentation has been identified within the social sciences as an important abstraction for explanations, at least when humans are concerned. So what we are trying to do, what I'm trying to do with my research and with my group, is to pursue this the view that argumentation can support explainable AI, and computational argumentation is amenable to provide explanations for techniques that are computational themselves. So just to, as already hinted at, actually there is already a lot of argumentation out there. This is an example in explainable AI, this is an example of a LIME explanation, one of the attribution-based methods. you can see that there is a specific input. This is information about a mushroom. We don't really care about what these things mean, but the task is one of classifying the mushroom as edible or poisonous. Lime would, the machine learning kind of classifier that is being explained here predicts that this is a poisonous mushroom with top probability. And the explanation here is about the features that are for poisonous and the features that are against poisonous by being for edible. So this is really, as I said, reasons for and reasons against. I would therefore say that these explanations are really bipolar argumentation frameworks, the way we call them. So there is already this kind of view, this kind of flavor in some of the work on explainable AI that we can leverage on. So there is a lot of work in explainable AI using argumentation, a lot of which I have done, but there are others working in this space as well. And the basic idea of explainable AI by means of computational argumentation is that you have a system or some data computing some outputs. And basically the task is one whereby you extract an argumentation framework which provides an abstraction of the debate underpinning the system, because the system is never, even when the probability computed is 1, there is never absolute certainty. Indeed, in the example we just saw, there was an argument, the reasons against the mushroom being poisonous. So the idea is that we can explain what the system based on data often is doing by abstracting an argumentation framework, and that's a very important step, provide argumentative explanations in formats which are amenable to human consumption, and that's where the social element happens. So this is the machine view, but this one here is the bit that thinks about the user itself. So taking into account also the social and human-oriented dimension as well. And argumentation is particularly amenable to human consumption because we are all quite used to arguing. And there are even psychologists that claim that we developed reasoning in order to argue. That's why we reason, nothing else. So this is the theory of Mercier and Sperber. So there is support for this view also from psychology. So there are 3 types of approaches within this scope. There are intrinsic approaches, whereby the models that are being explained are defined argumentatively upfront, and then the abstraction, the extraction of the abstraction is of course easier in that case, and the focus is more on doing this transition. But there are also post hoc explainable AI techniques using argumentation, which may be based on a complete counterpart of the method being explained or an approximation. And in all cases, no matter which approach we are using, by the way, we have a survey that we will present at ICHCAI, at the forthcoming ICHCAI, in which we overview this space. In this particular setting, we can see that the semantics plays an important role. For the intrinsic approach, the semantics of the argumentation is something that needs to be chosen so that it works for what you want to do. But in the case of post hoc kind of approaches where you have already a system, you can't choose the semantics. It needs to be what the system has. So it could be, the activation functions of your neural network if you're using a neural network. So the choice there is of the argumentation framework in such a way that that semantics has the properties that make the argumentation reasonable. So it's a bit of a reverse engineering kind of step. So I'm going to give you some examples of these. There are lots more I could give you, but I decided to choose a number of these. But before, let me tell you a little bit more about these properties. As I told you, one important property of argumentation semantics is this dialectical monotonicity, that if you add an attack against an opinion, the opinion is weakened. If you attack a stronger attacker, the opinion is even more weakened. And if you add a supporter, then the opinion is strengthened. And if you add a stronger supporter, it's even more strengthened. So this is something that from an explainable AI viewpoint is an important consideration to take into account if you want argumentation to explain what the system is doing. And in the specific setting of LIME that we saw before, this existing attribution-based method, this means that if we are, if we interpret, if we extract an argumentation framework from LIME, and for example, we say, let's focus on the stronger attacker and the strongest supporter only, as here. So this is a stronger attacker and this is the stronger supporter. This is our bipolar argumentation framework. This is attack, this is support. Then what we want to do is that if the strength of the attacker it grows, so it becomes a stronger attacker, we would want the probability of the prediction to decrease. So the explanation needs to be such that it has these desirable properties, because if not, it doesn't make sense argumentative. So it's not just extracting the argumentation framework, it's also making sure that these properties are there to guarantee that humans will buy the explanation. Okay, so I'm going to give you a bunch of examples. The first one is one whereby we define an intrinsic data analysis method, which is natively argumentative, but can be used for prediction. So what we have is a data set, which could be very large, and an unlabeled data point for which we want to make a prediction. So the data set has data points we labeled, so we know that mushrooms are edible or poisonous, and you have a new mushroom and you want to determine what is the class for that mushroom. So we first extract a characterization which shrinks the space, because you cannot have huge argumentation frameworks. We wouldn't make sense to humans. You need to be able to reduce the space. So there is a first step where techniques for feature engineering or dimensionality reductions that are developed in machine learning and data science are of course crucial. And then after we have extracted a more manageable representation, we extract an argumentation framework. We use here a module called argumentation debate miner. In this particular work, we use abstract argumentation, the simple kind. There is only attack. And what are the arguments in this case? So we have to decide what the arguments were and also how to define the attacks themselves. And we choose for arguments the data points. The labeled data points, if you think about it, are opinions. Each one has a label, and data points with different labels disagree. So there is an obvious source of disagreement. Of course, this would mean a huge disagreement space with lots of symmetric attacks, the way we would call it. So we need to be able to reduce this to a manageable level. And what we do is we use hyperparameters, which are a partial order over the data points, a bias. I don't want to give you the details, but this is just a bias. And in particular, a bias label, for example, poisonous, and a notion of dissimilarity between unlabeled data points and data points. And we use this to automatically extract an argumentation framework from which we predict and also explain. And the explanation can be in the form of disputes between two fictional players, proponents and opponents. I'm not giving you the details, they are well documented, but I'm going to give you an application. I mean, this is just an example of what happens. This is a very simple data set about music albums. These are the features, and these are the labels, the outcomes. We have an unlabeled one. And what we do in this case is we extract an argumentation framework where, as you can see, the data points are arguments, and they kind of help of these hyperparameters. With the help of these hyperparameters, we obtain very few dialectical relations. And what's interesting is that prediction then becomes identifying winning arguments, and in particular, identifying whether the default argument is. Again, I'm not giving you the details. I hope I've given you a feeling about what this is. But I want to tell you that we have actually applied these in practice for predicting and explaining the outcomes of bills going through the UK Parliament in collaboration with Thomson Reuters. This is a bit of a use of these techniques in a more user-friendly way. Each of these boxes is an argument. The edges are the attacks, and each of the arguments is a bill that has gone or needs still to go through Parliament. And the color tells you whether it did manage, so the label, whether it did manage to go through Parliament or it didn't manage to go through Parliament. And we can use these to predict whether bills will go through Parliament and also explain them. We don't have here any kind of an illustration or explanation, but already this kind of identifies what are the crucial features, in a sense, the features that make a difference in providing these disagreements. So these are a bunch of visualizations we can extract from these. As I said, we have done this in collaboration with Thomson Reuters, and we have carried out feature engineering with their help automatically by natural language processing in most cases. So the example seems simple, but it kind of worked well, both in terms of accuracy of predictions and in terms of explainability. So this was a workshop we ran with some parliamentarian as to whether this could be useful or not. Another example I wanted to give you is one in the healthcare context. You're doing a lot of research in healthcare. So this is one of the things that we have been doing within a project funded by EPSRC, which is the national body for engineering research. And we've done this in collaboration with medics from St. Mary's Hospital. So the problem was one of having a patient-centric reasoning and decision support tool for patients with comorbidities. We focused on COPD, which is chronic obstructive pulmonary disease. It took me a while to learn it. I hope I said it well. And these are patients that are chronically ill. So they have asthma, they have diabetes, they have all sorts of things. So you have a bunch of guidelines, medical guidelines that apply to them. And they are often in conflict. So doctors need to decide what to do and resolving these conflicts. So what we worked on was a kind of an automatic pipeline whereby guidelines can be computerized and then arguments extracted from these computerized versions of the guidelines and conflicts resolved to provide recommendations to patients. And an important aspect we had to take into account was that both patients and doctors have preferences. So the important aspect is also to take into account what patients and doctors prefer in many ways. So what we did is we used an ontological representation of guidelines done by people in the Netherlands. And they are basically providing recommendations, R1 and R2 here. One says the recommendation is that this particular treatment should be administered, and one says that this particular treatment should not be administered, and this treatment happens to be a special type of this treatment. So there is a conflict. So this is something that guidelines can be represented in, and what we worked on was the mapping of these into using knowledge into an argumentative version, drawing arguments from these representations, which are extracted from the guidelines themselves, and then use the semantics of argumentation to provide suggestive recommendations to doctors. So this is something that we are piloting now in Serbia, in Belgrade, with a bunch of hospitals, with a electronic health record provider there. The funding that we obtained was for collaborating with developing countries. We also had China and Myanmar Myanmar became a mess, and China as well, things didn't work out. So, but still, it was great that we could actually work with, with Serbia. So that's the second intrinsic method, which is natively kind of argumentative that we developed. And the last application I really wanted to talk to you about, and Francesca, I don't know how I'm doing with time. I'm doing very badly. Okay.
It's another 15.
Good. So the last thing I want to tell you about, which is generic, not specific to an application, it is really about explaining machine learning. As I said, one of the main motivations, one of the main reasons for the push for explainable AI these days is the fact that there are opaque systems that are very good at drawing patterns from data, but nobody can make any sense of what they come up with. And also, people don't quite trust them, and they don't trust in particular whether they rely upon biases, data have biases, and whether there is any artifact that they're using, etc. So this example I'm giving you is about a relatively simple neural model. This is a one-level deep convolutional neural network. So one of the simplest you can have, but still it is convoluted itself. So you've got an input. In this particular example, I'm using a text classification example. So I want to classify what this input text is, particular whether it belongs to, I don't know, business category or some other category. So it's a classification task. And what the CNN does is it uses an embedding, vectorial embedding of this text, which is then fed into the convolutional part, to which a max pooling is applied, and then fully connected layers with the softmax component is giving a probability for the various possible output classes. So it's simple, but it's already complex, and it's not clear why, given a certain output, we would, what is the reason behind this output? So what the majority of work in the literature, attribution-based, counterfactual, rule-based, do is that they go and look at the words in the input to tell you what is, responsible for. But arguably, I would say, at least in my mind, this is only part of the story, because you really don't know, even if you know what's responsible, you don't know why and what led you to that output anyway. So what we are doing argumentatively is trying to make the inner bits of the neural networks play a role and be part of the debate, because they are responsible for certain outputs to being computed. It's not just the inputs, it's also the inner workings. So what we have done in this particular example and in a bunch of other cases is extract an argumentation framework from this. And the argumentation framework is relatively simple. It's a debate between, with three layers. The inner bit, the thing that is really being debated is the classification. So in particular, one of the three possible here, the one that is computed, and that's that this is business. And sorry, this is a different input than the one I'm given here. I hope you get the idea. So this is the input words. Each word is an argument. Each word can play a role in determining the certain output. But the filters, these bits here in the middle, also play a role. And you can see that we have identified what each word supports in terms of filters and supports or attacks, and also what each filter supports or attacks in terms of the classification. So this is what we call a deep explanation. It's not just shallow inputs versus outputs. It's deep in going in, looking at the inner levels of inner layers of the actual machine learning technique that is being used. Of course, for this to be, as I said, making sense argumentatively, we need to decide when we extract this framework, what is the semantics that we are using to evaluate this, and the semantics needs to be one that makes sense in the context of the particular setup and that satisfies properties of argumentation that make sense to humans. So in this particular setting, we have chosen as a simple illustration an existing method for interpretability. This is layer-wise relevance propagation, LRP, and we treat it as a semantics. And it's the necessity to make this semantics satisfy this property that leads to obtaining these relations. So the relations are not obtained from the top of our head, are obtained so that this property is satisfied when this semantics is used. So we are deciding at the same time the semantics and the properties and the relations themselves. Of course, this is not necessarily something we can show humans, because it's something that makes a lot of sense to me and other computational argumentation people, but probably not very much to you either. And there is also an issue as to what filters represent to humans. I mean, they're not necessarily something interesting and kind of useful to the lay person. So the important next step that we need to do is one of extracting argumentative explanations from these. And these argumentative explanations need to be usable by humans. So that's the social element. We choose a certain interactive representation. So we extract this automatically from the argumentation framework given up here. So first we have to choose how we are going to show humans these filters. And what we decide to do is to actually use all the training data, passing them to the filters, seeing which data and which words in the data activate the most the filter, and we extract basically word clouds with n-grams to represent those filters in a way that humans can make sense of them. So, for example, here you can see that the most important, or here, for example, you can see that this is a lot about business. It's corp, a lot of it. So it's a filter that seems to have learned to recognize the concept of corporation. So it makes sense that this supports the classification business. And in the interactive version of this explanation, so each of the filters here is clickable. So you can actually see which words in particular are supporting, in this case, the filter. And this is about more military kind of stuff. And this is attacking the prediction of business. So basically, what we are trying to do is not just to tell you, these words here are responsible and these words here are against it. We're just trying to tell you how it works. So we are trying argumentatively to explain what goes on inside. As I said, this is a simple example, a simple machine learning classifiers, and there are others that we're working with. Neural networks are not the only form of classifiers we are considering. We are also working with Bayesian classifiers, and more recently we started working with tree-based classifiers as well. So this is just a bit more details as to how we obtained human-readable versions of the filters from pushing training examples through the classifier itself. Okay, so we are, as I said, doing a lot of work in this space. We, in addition to what I've just shown you, we are also working on Bayesian classifiers, and we also have argumentative variants of counterfactual explanations, whereby we use a notion of critical support that is basically the basis of counterfactual reasoning. What needs to be changed for changing the output. We are also doing a lot of work on explainable fact-checking. We extract debates and other types of explanations, including summaries from various types of text. And in particular, we have done some recent work on fact-checking in public health with COVID round. We all became we've all become more interested out of necessity as well. There is a lot of information out there. There is a lot of stuff whose veracity needs to be ascertained, and we have the need to explain why and how this is so. And then we are also doing a lot of work on using explanations for the next step, which is debugging models. In one of the main issues, I guess, that occurs in machine learning and data analysis is that you've got these models that may capture biases in the data or may incorporate artifacts which are specific to a certain data set. And when you want to port these models onto a different data sets in a kind of out-of-domain setting, the artifacts are in the way. So what we are doing, quite a bit of work we are doing at the moment, is using explanations as a way to, open the box and let designers and developers of models see what is wrong, and then inform the debugging of the models so that they are less biased or more portable, for example. I'm happy to give you details if anybody's interested, but that's all I'm going to say at the moment of this. What I wanted to instead tell you a little bit is also the human aspect, and the fact that there is a lot of need in this space to actually experiment with humans and see what humans want and what humans make sense of. So explanations are not, as I already argued, something that belongs to machines. Explanations need to empower humans. So an important line of research is one whereby you try things out with humans and you see what is useful to them, and in particular what they trust or what makes them understand better the system. So we have done a bunch of work in this space, for example, considering different formats of explanations that are drawn from the same argumentative frameworks. Some may be in tabular form, or can be textual, or can be conversational. And then we kind of engage humans. We mostly use Amazon Mechanical Turk for this kind of experiments to see what makes humans understand better what goes on. And you can see that the help of explanation is clear. That humans that are shown explanations understand a lot better what goes on, and there isn't a clear-cut answer as to what type of explanation they prefer. Some prefer tabular, some prefer conversational, which means we really need to support a variety of explanation formats if we want to capture different types of audiences. And this is another kind of question that you can answer. You can try and answer whether humans are satisfied or not. In this particular experiment, we use a recommended system for movies, and we use, as I said, Amazon Mechanical Turk. This is work we've done in collaboration with psychologists from University College London. Okay, so again, I could give you more details, but let's leave it to that. So I hope I have convinced you that one can use computational argumentation to empower various forms of explainable AI, going beyond what's out there. I have at the moment a bunch of projects looking at applications of this methodology in finance, in collaboration with JP Morgan, and in healthcare and law. This is something that will start in October, as Francesca mentioned before. And there is a lot of work to do in this space, and in particular, looking at more types of black box models, looking at more use of explanation for integrating feedback to debug machines. So to really have a human-machine partnership that would empower more applications and more uses, and of course addressing at the same time the problem of manipulability, because the moment people understand, there is always the sly one that tries to trick the system. So manipulability of the systems that are explainable is also an important question to look at. We have a lot more evaluations with humans to do, and a lot more argumentation to play with. Also, one of the things I really would like to do is to have a fully scientific theory of this notion of argumentative explanations that here, that is widely deployable. That's all I wanted to tell you. I can tell you more if you've got questions or if you have time. Thanks for your attention.
Just give me a second. Are there questions online? Not for them. Then please go ahead. If maybe you mind coming closer so that you can speak.
One of the concepts that are bound to explanation is causation. Important that the explanation provide is backed by real, and causation now can be handled with kind of calculus, things like that. From a certain viewpoint, it sounds quite conceptually similar argumentation.
Yeah, thanks a lot for the question. This is a very important point. And indeed, we are working a lot on using causal models as the starting point for extracting argumentation frameworks. The do calculus is, of course, great. Yeah, no, indeed, this is a great question. And when I talked about, so you're giving me an opportunity to say, yeah, so basically there is an important difference though. So causal models, the way I see causal models with my argumentative hat is that they only talk about support. They only talk about what is responsible for in a kind of, there is no disagreement, there is no debate. So you can still use, and indeed a lot of the attribution methods, the relationship between the attribution methods and causality is kind of unclear. So what we are trying to do is use causal models, and there are ways to extract causal models from other models. And there are also models such as Bayesian classifieds that come with a causal model underpinning them. So we are kind of using them as a basis for extracting argumentative explanations. But there is still a step to be done in going from the causality and the dialectical relationships. And this is nonetheless important because you want to try and identify not just what is responsible in a sense, in a positive way for, but what is going against, in a sense, a certain conclusion. So causal models are great and they are an important intermediate step for a lot of the work we are doing, but they are not the end of the story in my mind, because humans like also to see, the kind of, in a sense, what is not quite in line with a certain conclusion. So there is still a step to do, but there is an important contribution for causal models to make. And indeed, as I said, we are using them extensively. Thank you.
More questions? Posca, piace di venire qui se poi.
Thanks, Francesca, for the nice and inspiring talks. Indeed, there are a lot of joint potentiality for research. I was wondering about the last approach that you proposed, this when you try to use this interactive model. So this interactive model with the clouds that the user can explore the various. So I think it's still a little bit at the beginning, I have the impression that there is not really an advancement with respect to the features and relevance that they are doing with text. So the plans are to go forward.
Yes, absolutely. I mean, this, as I said, is a very simple example. And it's one that is a kind of a viability, kind of product, if you like. And indeed, we have considered a very simple, one level deep CNN. So, and we are also using LRP, and it's not obvious whether LRP as the underlying semantics is the right one to go for. So there are a bunch of other things we are doing at the moment. We are also working with images alongside colleagues who are doing medical imaging and trying to see what works in the context. So there is a whole, path to go. And in particular, there is also the question as to whether something new, which is neither LRP nor activation functions in the underlying kind of methodology is the way to go, whether we need to invent something extra. What is though crucial is that we can't do this on our own. We need to work alongside data scientists, and also we need to work alongside the quite large amount of work on visualization of bits of neural networks as well. I mean, here we invented our own method for visualizing the filters in the case of NLP, but there are lots of methods for visualizing patterns in images. There is work on image segmentation, for example, etc. So I think there is a lot of work to do. There is a lot of work to do in collaboration. And there is a lot of work to do also. I focus here on the human side of things, but there is a lot of work to do also on the machine side. And in particular, I know you do a lot of work on faithfulness, for example, of explanations with respect to the method that is being explained. And that's an important other aspect that needs to be taken into account.
Things that are relevant and maybe improving that, but at the end, the user may ask something more. Maybe you can remove some portion of knowledge, so that's why you'll have human in the loop within the learning process as well.
Yeah, so actually I have some slides. If we put the slides back, I can show you, because we have done some work in this space already. So we worked at debiasing and also artifact removal. So I don't know whether the slides can be put back up. In any case, so basically we have actually used the very simple architecture that's shown you, the text CNN, so in a textual setting, and we have shown the filters to users, and I think we used 10 users. Then we aggregate their opinions as to whether those filters were or not useful, whether they had biases or whether they were building into them artifacts. Then after we aggregated by simple majority voting the opinions of the various users, we didn't even retrain the network. We upgraded the parameters of the network and proved that the resulting debugged network is more. Yeah. Okay. Let me see whether that doesn't go. Who knows where it is now? I need to go a lot. And we actually showed that you get less. There's a lot of bunch of stuff in case questions were there. There's a lot of computer science. Yeah, no, I didn't show you. I listened to what you said. So sorry, it takes a while. Okay, sorry, almost there. Like accidentally is the last one. Okay, here it is. So this is the architecture that we have actually developed. This is all publicly available, so happy to use. And you can see that the user here is the human debugger. Here we treat the filters as global explanations, so just visualizing the filters. So the human debugger says, I don't think this is a good filter. And then we basically have a debugged model that we then try out again on the same setting. And you just show you the experiments. I said there is a lot. So first is a feasibility study. Let me go on. So this is the biasing. So we basically looked at bias, kind of nurses versus surgeon. There is a gender bias there. And then what we did with experiments with Amazon Mechanical Turk, we saw that by this architecture, this debugging architecture, we can actually reduce the bias in the evaluation set. And then we looked at data set shift again, and we saw that by, again, same kind of, same structure, we could lower a bit the performance on the original training data, on the original data set, but we improve the portability. So this is something, again, very preliminary because it's just one architecture, but it just shows the power of explanation. So I think explanation really is not just something that, you know, it is not just a little hat that you put on the models. It's something that needs to empower the humans to do more. Yeah. So humans can do more with AI if they go alongside it. So my idea is that they need to be empowered to understand, they need to be empowered to relate and to interact, and then they need to be empowered to inform and provide feedback on the explanations themselves and the techniques to lead to, to better models. Thanks, Francesca.
I'm gonna try a question now. Are you still okay? Can we insist?
Yeah, sure. Let's go on.
Which is kind of related. On the data science side, let's call it, a lot of attention has been put lately on issues of reproducibility and stability of analysis. So you can, do the same thing or approximately the same thing on the data and get vastly different outcomes. And this is, of course, a huge problem. And I was wondering, as you were describing both the attempt at building explanations directly from the data and the attempts at taking the outcome of a machine learning algorithm of some sort and produce post hoc an argumentative explanations. So have you ever tried to understand how stable the explanations are? I'm wondering if there could be sort of and of course you would need a metric to say how much an explanation has changed. I don't know if that's an easy thing to do or not, but it could be that somehow the models are highly unstable, but yet the final explanation that recapitulates them remains fairly stable.
Yes, absolutely. I mean, this stability is a very important problem of explanations. I mean, I think it is one of the things that people look at extensively. Some people call it with different names. So basically, this means you are throwing the same inputs to it, you always get the same explanation.
Or some perturbations, or you change some knobs.
Similar input, you get a similar explanation. Unfortunately, the majority of, I mean, not the majority, but a large number of methods out there are not stable. I mean, methods such as Lime, for example, based heavily on perturbations, are completely unstable. And pardon? Yes, indeed. I think that there is work on kind of stability, which is an important aspect. So in our cases, by design, because we are extracting these frameworks from the model, and it's that framework, that's it. By design, these are stable.
Okay.
Of course, the real challenge is extracting the argumentation framework, and as Fosca was saying, there is a question as to how much beyond the state of the art you can go, and how you can innovate and create methods that are more intuitive and more usable than others. But yes, stability is a crucial property. I would say, as is faithfulness. Another important property is how faithful the explanation is to the underlying method. And this is something that I'm particularly, with my logic hat, also faithfulness, in a sense, having something which is, sound and complete. I think it's something that really appeals to me. Something that is not just, happens empirically to work, but is provably, demonstrably corresponding to what's out there is also very important. And I find that lots of methods out there, maybe not yours, but lots of methods out there are not faithful either. So these are all important questions that need to be addressed. additional questions which not many people address is, for example, tractability of explanations, not solely in terms of computation, but in terms of cognition.
Yeah.
I mean, are explanation cognitively tractable? To me, this is crucial. You get humans, you get a doctor, you say, you know, this is a tumor. You can't show a huge network with millions of things. You can't show one. I mean, you need to find the right balance as to something which the doctor can cognitively appreciate, while at the same time being faithful. And this is a challenge and stable, because faithfulness and tractability seem to be going, you know, against each other. So there is a fine balance and a lot of work to be done together to understand what is really the right way to go about these things.
Ok. Giovanni, vuoi chiedere tu?
Yeah. Sempre in inglese, right?
Parla
Thanks
piano,
for
parla
this.
piano, parla piano, parla piano, perché abbiamo il volume a palla.
Thanks for your very interesting and challenging presentation of many items. Many of them are strictly related to the legal issues, to which, but that's my basic take. I have a number of questions, but I'll just ask one. What's your interest? The first part of your presentation was basically recalling directly argument mining, and basically the description you gave was reminding very much legal reasoning. It's a sort of non-monotonic logic. So I would like to know a little bit more on your work on argument extractions, and eventually, if in your project you were mentioning law, whether you are working on the extraction of arguments from legal texts beyond the prediction whether or not a bill would be passed, maybe using case law, for instance, decisions.
Yes, thank you. Thanks a lot for this question. Yes, absolutely. So first, let me say that, you know, a lot of computational argumentation has actually come out of non-monotonic reasoning. So it's not a surprise that I've given you the example I've given you. At the, you know, in the early days of computational argumentation, that was the main drive, you know, trying to rationalize a bunch of logic-based approaches to non-monotonic reasoning in a single coherent framework. And it is also true that a lot of that work was based on logical formulation done by hand, from which then arguments can be extracted, which is somewhat what I assumed. At the same time, there is quite a bit of work, and I am myself doing work in this space in collaboration with Ken Sato from Japan, on automatically extracting information from legal text, and both in the case law setting and in the statute-based law setting. In the case of case law, actually, the approach I mentioned that I illustrated with the passage of bills through Parliament, the original motivation for that work is actually case-based reasoning in legal settings. So each data point is a case in case law. And then you can basically understand relations between different cases, for example, by looking at specificity of features in cases as a drive to determine attack relationships. So we are doing that line of work automatically, or we're trying to, because it's not easy, using natural language processing. There are a bunch of very difficult sub-problems in legal setting. One is one of information retrieval. You first need to identify in large pieces of text what's the bit that you really are interested in, and what kind of information you are interested in extracting. So we are currently carrying out a labeling exercise in collaboration with Ken Sato, as I said, and a bunch of law students in Japan of contract law, for labeling first the relevant bits of the text in a way that will support information retrieval, and then we want to carry out argument mining, which is typically a classification problem in natural language processing. So you are typically training classifiers that are given pairs of texts as labeled pairs of text, some labeled as in an attack relation, some labeled in a support relation. So you train a classifier using standard deep learning models. These days, a lot of BERT, if you're familiar with this, and then you are trying to deploy that. So another area where there is an awful lot of work to do, lots of interesting questions, and again, the need to collaborate. You need to get lawyers talking to data scientists, talking to computational argumentation people, etc. There is a lot of interest in industry also in argument mining. I don't know whether you're familiar with the project Debater by IBM. They have a whole project mostly driven from IBM in Haifa on getting machines to argue. The whole, I mean, there's a whole group there that is working on that and several others in the world. So a lot of interesting work to do. I just wish we had more people interested.
Giovanni, vuoi fare un rejoinder?
That's okay. There are too many things to discuss. I mean, we are working on the same line here at Scuola Sant'Anna, but I hope we will have more opportunities to directly interact on these issues, because there is also all the line that you were mentioning, what are the legal constraints for transparency, traceability, and explainability, which is another area in which we are extensively working at the Scuola that would be good to talk about for possible collaborations. Thanks a lot for your presentation.
Thank you.
Ale?
The question is about the finance application.
So Alessandro wants to know more about the financial application.
Yes, so as I said, we have this collaboration with JP Morgan. They are extremely keen on explainable AI. They have a new center in explainable AI based in London. Interestingly, in finance, they have lots of regulations that force them towards explainability. And they have mostly tabular data. So the techniques that they're using are not deep, are not opaque. They are mostly used tree-based classifiers, XGBoost and this kind of stuff. So you would imagine that, right, those are transparent techniques, very interpretable, why bother? No, there is still an important problem of explainability in the context as well, because for something to be mathematically interpretable or understandable by data scientists doesn't mean that it's understandable to regulators or customers. So we started working on, as I said, tree-based classifiers, and there are already a bunch of approaches in the space, but there is, they are basically not happy with what's out there, put very crudely. So we are trying to identify really the properties that are important when providing explanation that would satisfy regulators. We are trying to understand what format of explanations are more amenable to different kinds of users. This is, as I said, mostly with tabular data, but we're also working on fact-checking for financial news as well. The project only started last autumn, so we are still at the beginning.
Is there another question? Vieni. Scusami, qui si fa ginnastica. Dai.
Francesca, very nice talk. One thing I wanted to ask you, a lot of let's say, the current methods for learning are, both in working with relational data, but also with images, sound, are somehow capable of finding concepts in the data that correspond typically to quite complex combination of the input features, right? This can also hold for tabular. So in that case, the argument of the argument network are not directly linked back to simple modalities on individual variables, right? But they're more elaborated. how do you, what's your take on that? How somehow feasible is to use, let's say, linking between the symbolic and non-symbolic part of the story to build, you know, really high-level argumentation? Would be a fantastic interface between models and the people.
Yeah, that's a great question. It is actually not easy. And that's why I said one needs to work also with people who look at interpretability of components, or concept extraction, etc. So what what I have shown you with the word clouds is our own take on one particular problem. But in general, there are two sub questions in my mind to your question. One is, do we want to work with methods that are more in kind of with versions even of opaque methods, but they are more interpretable. I mean, there is work, for example, in neural networks that lead towards a better separation of concepts across clusters of neurons than others. So that's potentially a better way to start. But in general, whatever you have, if you want to explain whatever you have, there is a question as to understanding conceptually what is going on in there. So we, for example, even with tabular data, we had, even with feed-forward networks, which are kind of semi-understandable, there is a huge problem if you have a hidden layer of some sort to understand how the input features are aggregated into these hidden nodes towards the output. So preliminarily, we work on, we have invented some kind of ring where you are introducing the dominant features, but it is a huge challenge. So again, it's not something I can tell you we absolutely know how to go about it. I can only tell you we are aware of the problem. And of course, there are variants of existing opaque techniques which may be more amenable to this stuff, but the question remains as to whether one can develop a generic methodology for empowering these abstractions.
Can take us. So before we clap again, I think Sabina would like to.
Thank you, Francesca, for your impressive presentation. I will switch to Italian just before the last sentence. Thank you to everybody for being this very interesting seminar. Grazie Francesca per essere qui, parliamo un po' italiano, visto che sei qui in vacanza per un paio di settimane, quindi possiamo anche parlare italiano. Siamo molto contenti e speriamo che tu possa tornare nel secondo semestre per fare anche un periodo di contatto con i nostri allievi e con i nostri PhD. Penso che possono nascere tantissime idee per collaborazioni e per scambi. Hai toccato una serie di esempi che in qualche modo hanno toccato le corde degli interessi di vari istituti, di vari gruppi di ricerca, e quindi penso che si possano veramente, si può partire con una serie di possibilità di interesse. E mi preme anche ricordare che parlando con Francesca ha dato la sua disponibilità anche per opportunità di tirocini e di scambi, sia a livello allievi che a livello PhD, quindi invito tutti i presenti a tenerlo presente, un gioco di parole, però se pensate che qualche allievo possa essere interessato sulle tematiche che Francesca ha oggi presentato, io credo che questo ponte sia molto importante da costruire, perché lo scambio può essere veramente di grande interesse. Quindi grazie di aver dedicato un pomeriggio delle tue vacanze, che sono sempre preziose, a venire alla scuola a conoscerci, e ti diamo due piccoli pensieri da parte nostra.
Grazie mille, non me l'aspettavo. È stato un vero piacere essere qua, grazie delle domande molto interessanti e condivido. Penso ci siano un sacco di opportunità di collaborazioni e opportunità, spero, di ospitarvi, o anche delle posizioni aperte, quindi se interessa.
Ora con quello andiamoci chiapa. Non ci portare via i nostri.
Grazie mille, grazie a tutti.
Grazie ancora.